Hey guys, so this is section 8.7. We're going to look at how the vapor pressure of a pure substance depends on the applied pressure above it. So let's start out by looking at this situation right here depicted by these pictures. So we'll start out with water at 25 Celsius, and it ends up that the vapor pressure of water at 25 Celsius is 0.0316 bars. We'll call that P star, because we have a lot of pressures floating around in this section. If we put a mass, okay, so we have our typical frictionless cylinder with a massless piston where we put a mass on it, and we put enough mass on to apply 1 bar of pressure. This is all going to be, the water will all be in the liquid phase, there will be no gas. If we look at the phase diagram, well, this is a generic phase diagram, but we can use it for water. At one bar, right here, at 25 Celsius, which is above the melting point, below the boiling point, we're somewhere in here. It's a liquid, all of it. Now, okay, if we take some of this mass away so that the pressure on top of the water is equal to its vapor pressure at its temperature, which is 25 Celsius, then we're going to have, well, where we'll be in this phase diagram is we've decreased the pressure at the same temperature until we got right here at the coexistence curve for water between liquid and gas. So there's going to be an equilibrium. There's going to be both gas and water. Now, the pressure will stay the same. We can change the volume, or the volume can change well, the pressure stays the same as long as we keep the temperature constant. We can see that if we look at the pressure volume phase diagram. So that would be the situation here where the volume increases, the pressure stays constant, this green line right here, and this green line is an isotherm, so it's the same temperature, and we're right in this area right here. Okay, so now we're going to take that and we're going to add some argon. It doesn't argon, just any inert gas that's not going to react with anything. And the point of that inert gas is to add enough at constant temperature to increase the total pressure inside of this to be equal to 1 bar. Okay. So now we've increased the pressure on this liquid to 1 bar. And what we're going to do is we're going to look at what happened to the vapor pressure of the water in this situation. So how the vapor pressure of the pure water depends on the applied pressure. The total pressure inside of here, called P total, is equal to the pressure of the water. PW is going to be P water for us plus partial pressure of argon. So what we want to do is we want to calculate what the partial pressure of the water is in this situation with the increased external pressure. So we're going to start out with the equilibrium condition, and that is that the chemical potential of the liquid must be equal to the chemical potential of the gas. This is the gas. And we're going to differentiate this with respect to the total pressure above the liquid. So how the chemical potential changes as we change the total pressure up here. So the partial of the chemical potential of the liquid with respect to the total pressure, and we're going to keep the temperature constant, so T is constant, is equal to the partial derivative of the chemical potential of the gas with respect to the total pressure at constant temperature. Now, we're going to pull a little fast one here. We're going to write this differential slightly different. This is exactly the same if we write partial chemical potential of the gas with respect to the partial pressure of the water at constant temperature times the partial of the water, the partial differential of the partial pressure of the water with respect to the total pressure at constant temperature. You see that these cancel and it's exactly the same. Okay. But, okay, now we know from section 6.2 we saw that d mu, the chemical potential, or dg, same thing, is equal to negative molar entropy dt plus molar volume dp. If we take if we basically take the set temperature constant, setting temperature constant dt is 0, so this term goes away, and divide through by dp, we get d mu, which is chemical potential dp, constant T is equal to, this goes away and we just get molar volume. So what that means for us up here, okay, so applying this to this right here, it says that d mu of the liquid over dP total, constant temperature, is equal to the molar volume of the liquid. And this one right here, it says that the d mu of the gas, dP of the water, is equal to the molar volume of the gas. So if we set these equal to each other and write them as molar volume of the liquid here, molar equal molar volume of the gas times this partial, looks like this. Molar volume of the liquid here is equal to the molar volume of the gas here times partial pressure of the water with respect to the total pressure, constant temperature. Rearranging this, that gives us partial of the partial pressure of the water with respect to the total pressure with a constant temperature is equal to the ratio of the molar volume of the liquid to the molar volume of the gas. So this is nice right here. So let's look at that. What does that tell us? It tells us how the partial pressure of the water above the liquid changes as the total pressure over the liquid changes. And it's equal to the molar volume of the liquid over the molar volume of the gas. Now we know that the volume of the liquid, the molar volume of the liquid, is a lot smaller than the molar volume of its gas. So this ratio is a small number, which says that it tells us right from the get-go that it doesn't change much, but it does change some. It's not zero, right? So we're going to see how much it does change. And to do that, we're going to apply the ideal gas law. PV equals nRT. If N is 1, then P molar volume equals RT. Solving that for the molar volume equals RT over P for the water, for the gas rather. We're going to replace the molar volume of the gas with RT over pressure of the water. So there's the pressure of the water, which is right here, and there's RT, which is right here, and all this is replacing this. Rearranging this and making them exact differentials, we see that bringing this over here, bringing this derivative over here, RT over the partial pressure of the water, D partial pressure of the water, is equal to the molar volume of the liquid, D total pressure. Something we can integrate, so we will. So we're going to integrate the left from the vapor pressure of water at that temperature to the vapor pressure of the water under the new pressure. And that's dPW over PW equal to molar volume of the liquid. Integrating this side, integrating from P star to P total, which gives us RT ln of PW over P star equals the molar volume of the times the total pressure minus P star. Okay, so there we go. That's something we can use. That's going to let us calculate the partial pressure of the water under the total pressure when it changes. So let's do that. So remember, okay, this is a picture right here that we're talking about. Total pressure is the pressure inside of here, which is going to be the same as this mass. P star is the vapor pressure of water at 225 Celsius, 298 Kelvin. So it's 0.0316 bars it ends up, or 3.16 times 10 to the third pascals. In our situation here, the total pressure is 1 bar, or 1 times 10 to the fifth pascals, and our temperature 298.15. The molar volume of the liquid, we need that. It's water for right here. All we do is take the molar mass, use a density. We're going to not go past 3 sig fig, so it's good enough to call it 1 gram per milliliter, and convert that to cubic meters, and we get 1.8015 times 10 to the minus fifth cubic meters for the molar volume of the water. All right, good. So now, guys, we have enough to plug into this green equation up here. So this is the molar volume of the liquid. That's R. That's T. This is total pressure. This is the vapor pressure of water at 25 Celsius, 298 Kelvin. And check my math, but I think when you plug that in, I got 7.037 times 10 to the minus fourth. That's equal to natural log of the ratio of the pressures. Taking E to both sides, see the ratio of the partial pressure of water to the partial pressure of water by itself is equal to E to that number, which is really, really close to 1, which means that the partial pressure of water under that an external pressure of 1 bar is basically the same. Little difference out here in insignificant figures. But Let's look what happens when we increase that total pressure, the external pressure. So let's say it's 200 bars, right? That ends up being like 2 times 10 to the 7th pascals. Plugging that into the same equation, we get the natural log of the ratio of the pressures is equal to 0.1453. Taking e to both sides, we get that the ratio of the pressures is equal to 1.15, or the partial pressure is now 0.03654 bars, which is a almost 16% increase. That's significant. And there you go.